Welcome everyone to the ITC lunch. We just heard an excellent colloquium by Gnedin, who is sitting at the end over there, and he will talk a little bit later. I wanted also to apologize that next week I will be away. I'm attending a conference called the Falling Walls in Berlin, Germany, and I'll be speaking about breaking the walls of the solar system. But this conference, those are broken. Another announcement is that, and so Ramesh Narayan graciously agreed to sit here, change his angle, viewing angle, and one time, Ramesh, just one time.
It's going to be a real pain. It's such a great speech.
I just wanted to mention one other announcement and introduce Professor Xing-Wu Zheng, sitting over there, who is visiting us from Nanjing University. And this is his 13th visit to the CFA since 1982. And he is now working with Mark Reed on Bessel, which is, you want to say what Bessel is, Mark?
Mapping the Milky Way.
Mapping the Milky Way. So welcome for the 13th time, and we look forward to seeing you around. So the speakers today will start with Mia Imara, our own. She's, as many of you know, John Harvard Distinguished Science Fellow here. And she's also giving the CFA colloquium later today. And she will tell us here on X marks the spot or star formation. Then we'll hear from Gnedin that will tell us about Courant-Friedrichs-Lewy condition. Even textbook truths are worth revisiting, which is certainly true. And then from Christopher Moore, must be somewhere, talking down there. He will talk about magnetic field morphology effects on the determination of oxygen and iron abundances in the solar photosphere. And finally, Daisuke Nagai should be here from Yale, over there, and he will tell us about the physics of galaxy cluster outskirts. We'll start with Nia.
Good afternoon, everyone. My name is Nia Imara. I think there may be a few of you here who were present during my very first ITC Luncheon talk. And at that time, I was talking about a very strange molecular cloud having a very low level of star formation activity. And today, I'm going to be telling you about a very strange molecular cloud having a very low level of star formation activity. But it's a different talk, different cloud, different talk. And this was work that I conducted with Charlie Latta and John Lewis, both here at the CFA. So the emerging consensus is that filamentary structure is a prerequisite for star formation. Molecular clouds, the sites of star formation, are hierarchical in structure, and they're threaded by these long, skinny, dense objects we call filaments. Filaments have the potential to form cores, which can reach even higher densities, some of which reach densities so high that they can go on to collapse and form stars. Simulations of supersonic turbulence have consistently shown that gas is rapidly compressed into hierarchical networks of sheets and filaments. And when gravity is added to turbulent simulations, the denser regions can undergo gravitational collapse. And there are many sources of supersonic turbulence, including shocks in the spiral arms, where we find most of the molecular clouds in our galaxy, expanding H2 regions, gravitational instabilities, Rayleigh-Taylor instabilities, and so on. Observationally, filamentary structure has been known for quite some time, even if the lexicon hasn't always been with us. This is a plate from Barnard's dark catalog, or rather Barnard's catalog of dark markings in the sky, and I couldn't resist showing his hand drawing of the region. And you can certainly make out the filamentary-like structure and extinction here. And this was 99 years ago, but since then there have been many observations in the optical, infrared, and submillimeter that have shown us that nearby star-forming regions all have filaments. Now, what Herschel did that was new was really draw our attention to the fact that filamentary structure in the interstellar medium is ubiquitous, and that filaments have a number of uniform properties. Moreover, Herschel focused our attention on the idea that filaments are necessary for star formation. Now, more recently, but prior to Herschel, Phil Myers here at the CFA was one of the first to recognize the importance of the spatial arrangement of filaments. He coined the term hub filament network, in which you see these radiating filaments extending from a central compact high column density region called a hub. And moreover, Phil had the insight that most clusters, that the preferred environment rather for cluster formation and massive stars is at the intersection of filaments in these hub-like regions. He compiled observations showing that within 300 parsecs of the sun, all of the young clusters are associated with this hub filament-like morphology, such as in this example of Serpent South, and a couple more well-known examples, Barnard 59 and IC 5146. Now, the California molecular cloud is a really wonderful test case for exploring the relationship between filaments, hubs, and star formation in a relatively simplified environment. Charlie Latta and his collaborators discovered California in an extinction mapping survey of the Perseus region. And it's really interesting to compare California with Orion A, which is the nearest region of high mass star formation and which is often considered sort of the prototypical molecular cloud. So California and Orion A are at very similar distances. California has similar morphology, size, and mass to Orion A. But its star formation rate is about an order of magnitude lower than Orion A. And it has just one massive star, a B star, that's associated with a fairly humble cluster of about 100 members or so. And so we investigated a subregion of this cloud, and we were motivated by the question, how does cloud structure influence star formation in its embryonic stages? And again, this was work conducted with the CFA's very own graduate student, the one and only John Lewis. This is a 13CO map of the region, and you can start to make out these long, skinny structures. Now, Alyssa Goodman was one of the first to demonstrate explicitly that if you really want to trace out the full column density structure of a molecular cloud, you want to use dust as a tracer, because dust probes a much larger dynamic range of column densities than molecular line tracers like CO. And indeed, when you look at a far infrared column density map made from Herschel data, you see that the filaments become much more prominent. And these guys are extending from this high column density region in the north, which is embedded with two low mass sources. And because of the sort of cross morphology of this region, we've dubbed it California X. So we can use the dust map to determine the mass and other properties of the filaments. The mass of this entire region is about 2,000 solar masses. And we find that the mass per unit length of each of the filaments, this guy and this guy, is greater than the critical mass per unit length for an isothermal cylinder. So according to this criteria, the filaments are thermally supercritical. And the reason why this is an interesting exercise is because according to theory, when filaments become critical, they can start to form cores. And indeed, we identify a number of cores outlined in heavy black here. Each of these guys have radii of about a few tenths of a parsec, and they're on the order of 5 or 6 solar masses each. We also identify a couple of cores embedded in the hub in the north. Now we can use the 13CO observations to tell us about the kinematic structure of the cloud. We took spectra all along various positions along the filaments, and we fitted the spectra to determine the radial velocities represented by the colors of the circles, and also the velocity dispersions represented by the size of the circles. And what we find is that California X has this beautiful velocity gradient that's suggestive of an inflow of gas toward the north. Now, by multiplying the infall speed by the mass per unit length, we get a total mass inflow rate of about 50 solar masses per million years. And if the mass inflow rate were constant in the past, it would have taken about 3 million years for the cores in this hub region to acquire their present mass. And if the cores are moving at the same infall speed as the rest of the gas in the filaments, it's going to take them from about 1 to 5 million years to rain into the high mass clump in the north. But this is longer than their free fall time. So this is interesting because that means that if the cores are gravitationally bound, some of them are going to probably form stars first. Now, this project was essentially about the role of substructure in star formation. But in recent conversations with Charlie, I've been thinking a lot about cluster formation. And of course, that's an important question because most stars form in clusters. And there's two general scenarios of how clusters form. There's the slow cluster formation scenario and the fast cluster scenario. In the slow formation scenario, the formation time is several dynamical times, compared to about 1 dynamical time in the fast case. And in slow cluster formation, the clump gas has to reach equilibrium, and runaway gravitational instabilities occurs on much smaller scales than within the protocluster gas than the entire hub itself. And in the fast case, the gravitational energy of the protocluster gas is greater than the kinetic energy. So in this respect, it's subvirial or cold. And in the slow scenario, star formation is a local process within the protocluster gas, whereas in the fast case, stars form due to global collapse that can't be stopped by feedback. And so although we can't rule out slow cluster formation in the case of California X, the infalling filaments is pretty good evidence that supports the cold formation scenario. And I found this pretty recent paper on cold cluster formation by a graduate student at the University of Michigan, Alexandra Kuznetsova. And what I really like about this simulation, although I'm not sure that it was her original intention, is that as the gas evolves, you can sort of see the sink particles traveling along the filaments, similar to what's happening in California, potentially, and glomming together in these hub-like regions. And so to give you a few points to take away, not only do we see hub filamentary structure in massive clusters, but we see it for small groups of stars, such as in California. We find that hubs can grow by the accretion of mass funneled along filaments. And it may be the case that all of this gas being funneled isn't, or all of this mass isn't in the form of gas, that some of the mass being accreted is in the form of stars. In other words, it may be that all of the stars aren't forming in situ inside of hubs. And a very natural follow-up that we've been discussing is to investigate other regions of the California molecular cloud with varying levels of star formation activity to explore the evolution of filamentary structure. Thanks. Yeah, I think Avi is advertising our paper on astrophysical Russian dolls, where we use the Russian dolls as a metaphor for phenomena like filamentary structure or disks and spirals that occur on many different scales in the universe. Yeah, definitely. And turbulence. Yeah.
What little I know about it doesn't contain significant numbers of OMP stuff.
That's correct.
What's Orion A is the prime spot. So are these filamentary structures present in the region like Orion A?
Oh, they're absolutely present in Orion A, and I think what we can speculate about is that perhaps the formation of more massive clusters is a scaled-up version of smaller group formation like we see in California. Things are happening on different size scales, no doubt, and probably different time scales too. But that's definitely something that we want to explore more by looking at how the structure varies within California itself.
Do you consider how these filaments come into being themselves? I mean, you're sort of taking in what you presented today, their existence as an ab initio condition, but might their formation process also be a part of this story?
Might their formation process be?
A part of this story?
Oh, I think absolutely yes. I think our best sort of evidence for how filaments form is through simulations, and they show that very quickly. That first of all, that star formation happens very quickly after a molecular cloud is formed, and that supersonic turbulence is probably the main sort of culprit responsible for sweeping up the gas into sheets and filaments, and even causing hubs to form at the intersections of filaments.
But if we wait a million years, we see last question, Eric?
Yeah, I was just following up on that question. I was wondering what is it that defines a filament? And there's identified three concepts of filaments in your talk. And one of them was the notion that you have supersonic turbulence that compresses the gas momentarily. And then secondly, there was a 10 solar masses per parsec average density, which is a hydrostatic filament. And then finally, there's this hub and spoke thing, which you might think, say, well, it's like the process of spaghettification in black holes. Where you're stretching out a clump as it's being accelerated in the gravitational field. So what is there one kind of filament, or are there three kinds of filaments, or more, or?
The sort of working definition that I use is that this is an object that's overdense compared to its surroundings, and it has a high aspect ratio, so at least 5 to 10. And we see them all over at many different size scales. So the objects that I was showing you here, they're about 2 parsecs in length, and that's sort of puny, I would say. And of course, we have people here, Alyssa Goodman most prominently, working on the Nessie filament, which is maybe hundreds of parsecs long, but it meets the basic criteria of being overdense compared to its surroundings and having a very high aspect ratio.
Long as it's longer than it is wide.
Long and skinny and dense, yep.
Let's thank Mia and the audience.
Well, I wasn't sure what to expect, so I'm sorry if this talk is too technical. I will be talking about technical things. Are we going somewhere? Okay. So we'll start with computational physics. Now, 100.1, not in 101, it's 100.1. Really, if you think about how we solve equations, partial differential equations, in the simplest way, we discretize them in some way, say on the grid. So at some particular spatial and temporal, spatial locations and temporal moments, then we approximate derivatives with some finite differences at the time step delta t, grid spacing delta x, we plug them in, and for this very simple equation, we can come up with a solution, we can write the value at the next time moment as a function of the values at the previous time moment. That's what's called an explicit scheme, right? Because you explicitly express the values of future as the values in the past, and then you can solve it one step at a time and find a numerical solution everywhere in space. So for this, turns out that for this scheme to be stable, to actually get something, there has to be a criterion, which I will call for now a local time step constraint, and that the time step cannot be too large. So it has to be less than delta x divided by this velocity v, absolute value that enters the equation. And that's been known, and everything I'm going to tell for now has been known for 100 years. But it turns out it's not just enough to be stable. You can have a numerical scheme which is stable, but if it converges to a wrong solution, then you get a wrong solution. So you also have to converge, right, to the correct solution. And the main paper in this field is something which is a paper which was written by Courant-Friedrichs-Lewy in 1928, which they formulated what we now call Courant-Friedrichs-Lewy condition for convergence, right? But in many textbooks, your open textbooks, you see this condition to be called, Courant-Friedrichs-Lewy. I will call it CFL because everyone calls it CFL because no one wants to spell those long names. The condition actually you can express in words. It says a full numerical domain of dependence must contain the physical domain of dependence, and that's easily expressible in the sort of time-like general relativity time-like diagram. So that's your physical past-light cone, and this is your numerical past-light cone. And in a simple way to explain it is that your numerical scheme should be able to capture all the physical speeds of all the physical waves that you have, right? So if you want to track a shock wave that's going at 100 kilometers per second, and the numerical scheme can only transfer waves at 10 kilometers per second, you're clearly doing something wrong. So what it says is that all the speeds that physically present in the solution should be captured by the scheme. But this condition is manifestly non-local because it deals with sort of past-light cones. So this is the difference between something you apply locally to something has to be applicable to the whole to the solution in general. And the reason why it matters is that let's consider a very simple physical problem. Right? We have a point explosion. It's called sometimes Sedov-Taylor solution. You have just one bomb going in a uniform medium. As the bomb goes on to create the shock wave, this is a density plot. So it shows the density. This is under dense region. This is uniform, very cold gas outside it. So the shock wave going out spherically, the gas inside is very hot. So the time steps here are actually very small. If you want to calculate it numerically on this uniform grid, then your time step will be set by what happens in the middle. But all this gas outside is very cold. Right? Its local time step condition is very, very relaxed. Right? It can go, nothing changes there, so you can advance in time at arbitrarily large time step, essentially. And so, generically, if you're thinking about solving equations numerically on grids, if your time step is tied to spatial structures, so if you have uniform time steps or uniform grid, or if you have adaptive mesh refinement, it's more complicated. Your time step varies, but it's also a graded scheme. It's related to spatial refinement. So then, at the end, you have one cell that's which CFL condition will set the time step for the whole grid. Right? So, from a physical sense, if you're modeling the universe, you can have one supernova explosion in one GMC, in one galaxy, which will dictate how the rest of the universe should evolve. Right? And so what we should say about this? We live in a democratic society, should not have that concentration of power. So the goal is whether we can break it. So our goal was to try to figure out whether we can break it and whether we can allow different regions to evolve on their own time scales, but at the same time satisfy all those conditions. So if you think about that, this local time step condition, I call it weak CFL relation. Right? Let's say we have two different regions. This one is hot, this one is cold. So this green lines are characteristics. Right? This is space and this is time. So it's space-time diagram. It's hot means the sound speed velocity here is large. It's cold means sound speed velocity is small. Small means more vertical. Right? And so if we only care about this condition, then we can allow, say, this cell jump right here because we want to capture this characteristic. this one has to jump here because we want to capture this characteristic. So this one has a much smaller time steps than this one. So it satisfies the local time step condition. But now what happens if I send the wave? So the scheme in this case will be stable, but it's not accurate in the sense if I have a wave that propagates through the cell, enters this boundary, now it has to wait here, because this one goes from here to here without stopping. And so my wave, instead of going normally, having this very weird time step sort of shape, right? And it's kind of delayed, and the interfaces in which you change the time step. And the way it looks like in real simulation, that's a zoom into this point explosion. Again, this is shock wave, this is density. This is unshocked region, this is shocked region. So this is just a shock wave propagating across this. And this is this local constraint only. This one is the correct solution, the one that treats all the time steps correctly. I will show you in a second. And so you can see what happens, how these delays at the boundaries happen in this case. So for example, here, this wave wants to enter this boundary, but these steps, the small time step than this one, and now it accumulates at the border, and then cuts crossing. So it passes here, now it's going to happen in this place. So you get this kind of numerical artifacts. They're not actually that bad because they disappear with time. But if you want to have the correct solution at all times, you have to worry about this sort of piling up of stuff when you change your time step on the borders. And one way to solve it is to really make sure that even if the true characteristic here is this one, it sort of tries to capture that one, the one that the neighbor has. So that's one way of doing this. And in fact, in this case, we will capture the wave correctly. And some codes actually do that. So it would require this particular region to make more time steps than it really wants, but it has to do it to make sure that information from the neighbor propagates correctly. It turns out that it's even more complicated than that, because you can have things like this. So let's say you have, again, two regions, and this one goes with a long time step. It's cold one. This one is sort of warm. It goes with this time step. And then something happens. Let's say supernova explodes. When supernova explodes, this will have to go with even smaller time step. It has to drop its time step to account for the high temperature in this region. And now to avoid these problems with the border, there's these waves sitting on the border and waiting for the custom clearance or something. Then, in this case, you have to take this time step and reduce it to this point so they're matched in time perfectly. So when you do this, then you get all the waves correctly. And the reason to do it is because at the end, you actually save an enormous amount of computing time. This is comparison of what you gain when you try to treat all these time steps. When you allow each region to go with its own time step, this is a ratio of whole clock time, which is actually time you sit and watch on the walk on the wall and see how long the calculation took compared to in case we have uniform grid with uniform time steps. And you can see you're gaining factor of 10 or at least factor of 6 in many of those cases. And so the summary is that something that doing this we kind of discovered, and we were uncomfortable because we didn't read about this in the textbooks that existed for 100 years. But nevertheless, we now think there are two different conditions. Right? There is this local time step condition that requires for stability, and this safe condition that required to maintain correct speeds. Right? And those two coincides only for schemes with uniform time steps or for specific adaptive mesh refinement schemes. And so if you want to enforce to make sure that the safe condition is satisfied, all the waves propagate correctly in the code, that it's possible but requires some regions to move with smallest time steps. You have to lose some runoff launches, except this one. And it also has to be proactive. Right? So the scheme must allow for the regions to affect those in other regions on the fly. So that's actually all. Oh, wow, perfect timing. Right? So again, I apologize if this is too technical. It's supposed to be theory and computation. Luncheon, right? So, yeah. Well, I think even relativistic codes actually use time as time nowadays. I think most of them are now done as ADS. I don't know much about relativistic codes, but I think that most of them actually split that space-time into 3+1, even those which model black holes. So someone might correct here because so I think even they treat time as time. Yeah, and in applications for normal well, it's for normal gas dynamics. You really cannot do it because of this C4 condition, because you don't know what your time step should be until we got there. Right? And if you have a supernova explosion somewhere at later time, right? If you cannot predict where exactly it's going to happen a priori, which you actually need the simulation to make a prediction in the first place, then you cannot tell how to sample the time axis.
What do you think about one problem with taking like a global time step in addition to the efficiency is that you're subcycling many zones more frequently than you need to and accumulating essentially rounding error?
Yeah, that's another.
How does this affect like the convergence of a global solution?
Well, in general, you don't want to do this. Also, in practice, I didn't find any cases where it was bad.
Okay.
So, but yes, theoretically, you actually want to step with as large the condition as this local stability condition allows you, because formally, if you take a numerical scheme, expand it into Taylor series, you find that some terms disappear in this case, but not all of them. So.
Any other comments or questions? So one thing I'm wondering, so you're essentially waking up dormant cells when you realize they need
Yes, yes, you have to do something like this, yes.
Can you make a comment on higher order reconstruction?
I don't think higher order I don't think that it's in any way related to reconstruction. You can this can combine with any order of reconstruction. I don't think reconstruction is.
You have to save your initial states, or you.
No, because you only fire your Riemann solver at the endpoint. It's not related to reconstruction. So in this case, your Riemann solver is fired at this point and it uses this time step. It's all fine. Reconstruction fine. I didn't think deep about it, but I don't think you lose any order of this.
Okay, well, let's thank you for
Give me a second while I get settled. So can I start? Thank you for the opportunity to come and speak here at the ITC colloquium. I've been to, the luncheon, not colloquium yet. One day in the future. I've been to other seminars here at the CFA, because this is my first year here, but I have not been to this one, so I did not realize how many people showed up. So this is actually a good turnout. I'm actually more excited now to come speak. My name is Chris Moore. I'm a recent PhD recipient from the University of Colorado Boulder. This is my first year as a postdoc here at the CFA in the Solar Stellar X-ray group, which is in the head division under the tutelage of Catherine Reeves, Ed DeLuca, and Leon Golub. And most of my PhD research and the current research that I'm partaking in involves data analysis and instrumentation. But since this is called the Institute for Theory and Computation, I thought that I could talk about some numerical simulations that I analyzed as a graduate student. And so thus I'd like to acknowledge the individuals that contributed to that research that are not here, and locally, but they're in Boulder. So Matthias Rempel, the numerical simulations I will be discussing, he created them. Hein Uytenbrück created the radiative transfer code that I used to analyze the simulations, and I'd like to acknowledge my advisor for that project, Mark Rast, and advice and guidance from Serena Criscoli. And so I'll be talking to you today about magnetic field morphology effects and determination of oxygen and iron abundances in the solar photosphere. So one can ask, because we're currently, before I started this project, the question will still arise that we were unsure how a small-scale magnetic field structure played a big difference in spectral line formation and also the elemental abundance determination that you derive from fitting spectral lines. So that's the question that we set out to address. Essentially, it was like a master's thesis type of project. And one can ask, why do we care about elemental abundances for the sun? Well, in particular, many analyses in astrophysics are dependent upon accurate and precise determination of the solar elemental abundance. For example, temporal analysis of the local interstellar medium is dependent upon this because the solar elemental abundance is used as an initial start. What the elemental abundance is locally, you can compare this with local B stars to see how this has evolved over time. Galaxy evolution models nominally use the solar metallicity and supermassive black hole radiative processes, emission line models, and essentially this is critical for feedback between the supermassive black hole and its circum-environment. Opacities are strongly dependent upon the metallicity. And oxygen, for this study, like I mentioned before, we analyzed two elements. One is oxygen, which is the third most abundant element in the universe. So that's pretty important. And the second is iron, which is the reference metallicity element. So like I mentioned before, this analysis focuses on the solar photosphere, which is the region in the sun where energy transport transitions primarily from fluid motions, convection, to radiation. This is about 500 to 1,000 kilometers thick. We can calculate the emergent intensity using radiative transfer, which is strongly dependent upon the local opacity, which is a function of temperature, pressure, and density. And the main aspects of the opacity that we care about for the study are the continuum and line opacities. This is an observation of the sun in the photosphere in visible light. And for example, Earth for scale is the size of my pointer, it's a little bit bigger than a pointer here on this resolution screen. So that gives you an idea of how big the sun is compared to the Earth. And my simulations, for example, that I analyze are the same size as Earth. So we're looking at a very, very small patch at sun center. So recently in terms of the early 2000s, hydrodynamic three-dimensional simulations were used to analyze solar elemental radiative transfer and elemental abundances. This allowed us to more accurately investigate variations in opacity due to temperature, pressure, and density. This leads to highly corrugated surfaces if you use an equal optical depth surface. When you map this, the granulation pattern dominates the heights at which equal optical depth surfaces reside. This has profound impacts on the solar spectral lines. So for example, if we compare our three-dimensional hydrodynamic simulation spectral line compared to a 1D spectral line, we no longer need artificial broadening, micro and macro turbulence. So for example, the three-dimensional line is less steep than the one-dimensional line. It has a more realistic spectral line profile because the velocity flows are intrinsic within the simulation. So there's no need for this after-the-fact modification. So this inclusion of three-dimensional hydrodynamic simulations coupled with new updated information on atomic parameters led to downward revisions in carbon, nitrogen, and oxygen. These are critical for many analyses. And oxygen was a big one, a factor of 2, which is huge. And that led to disagreements with helioseismic observations and estimations of the sound speed in the core of the sun out to the solar photosphere. So now with these newer downward revisions, there are huge disagreements in what the sound speed should be as a function of radius, as inferred from helioseismology. So the question is, can magnetic fields recover some of this downward revision in terms of the spectral profile change when you analyze that and compare that with actual observations from your numerical simulations? Does that recover some of this negative downward revision in this case. I call it negative or positive. Negative means less elemental abundance is needed, positive meaning more. So when you think about magnetic fields, traditionally for the sun, for the photosphere, we think of sunspots, but we're not focusing on these larger concentrations. It's been pretty well studied to that point. But we're focusing on this smaller region, again, a little bit bigger than Earth for this yellow box here, where we see there's a radiative enhancement, this web-like structure, which is ubiquitous across the sun. This is due to smaller scale vertical magnetic field, which concentrates in the downflow lanes, which are called intergranular lanes. So these are proxies for a magnetic field in continuum intensity, and they're proven to be connected to kilogauss vertical magnetic field. So if we zoomed in on that yellow box, we can zoom in on this smaller red box, which is the size of the simulations that I analyzed, 6 megameters cross-sectional area, 8 kilometers spatial sampling for the simulation. And again, we can address the small-scale unresolved magnetic fields, significantly impact the spectra, and hence elemental abundance determinations. We do this by directly investigating magnetic effects, such as the Zeeman effect, modifying the opacity in the presence of a strong magnetic field, and also the indirect magnetic effect, which is the change in the thermodynamic structure of the atmosphere due to the presence and morphology of the magnetic field. We do this by examining 3 different numerical simulations: a pure hydrodynamic simulation, which is our reference, and we compare our 2 magnetic field simulations with this hydrodynamic atmosphere. Now, it's important to note that these 2 magnetic simulations have similar amounts of total magnetic field. The main difference is the morphology is different. For the local dynamo, we insert a seed field of 10 to the negative 3 Gauss. We allow the shearing velocity flows to amplify the field, a small-scale local dynamo. And on average, spatially, the positive and negative polarities are so close that on average, they average out and they cancel out to 0. So visually, it appears similar to what you see here, where if we naively look at this region in continuum visible light, we would say there's not much magnetic field there, but there actually can be, because the sun is magnetized on the large scales down to the small scales. The mean field poses an 80 Gauss vertical field, and that's similar to the faculae that you see here. So we have these simulations. We then perform spectral synthesis, vertical line of sight. To make things simpler, we did our first runs with local thermodynamic equilibrium, LTE, to investigate oxygen and iron, 5 lines of each element. And we calculate the equivalent width from the spectral line, and we compare this to the hydrodynamic atmosphere with the same lines where we forward modeled changes in the elemental abundance for the linear portion of the curve of growth. So we calculate equivalent widths here, compare it with the hydrodynamic forward model values to estimate at total elemental abundance deviation that would be inferred if you did not have this information in your analysis. So to narrow home the point that these 3D magnetohydrodynamic simulations are fairly different. For example, in the local dynamo, spatially average 0 vertical magnetic field, while the mean vertical field is similar to this, vertically imposed 80 Gauss field. Now, if we take an equal optical depth surface slice, we can see that the local dynamo has more dispersed field, but it primarily collects within the intergranular downflow lanes. Similarly here for the mean field, but there's a contrast, the stark contrast in the total magnetic field. So these are the huge 1,000+ Gauss vertical magnetic flux tubes that you saw before. And since this is such a short talk, I'll skip straight to the conclusion, which was there a huge impact? In terms of the local dynamo, the small scale fields, the answer is no, not really. Fraction of a percent and a few percent for iron, factor of 10 difference. And for the mean vertical field, it is actually a bigger difference, few percent for iron and a substantial effect for iron and a small percent for oxygen. So this is important. The morphology makes a big difference. It's not just do you have magnetic field or not. It's how is this magnetic field organized within the spatial region that you are analyzing. That's pretty critical. And we can look here at deviations in the hydrodynamic atmosphere, which is the black spectral line, compared to the local dynamo, which is the red line, which has a small difference, but it's asymmetric. And the mean field has a symmetric change in the spectral line profile. And so I had a nice little video to summarize why this is the case, but I just kind of ran out of time. So the question is, do you all want me to talk for 1 more minute to briefly describe this, or do you want to go straight to questions? So I'll go ahead. So I'll run it back real quick. So one way to think about spectral line formation is looking into the atmosphere as an observer, and the continuum opacity is dominated by the H- ion. So you see to a certain depth in the atmosphere. As one probes in different wavelengths closer towards the line core, you have increased probability of a transition, more opacity, thus you probe higher layers of the atmosphere. So the continuum, the wings are deeper in the atmosphere, the core is higher up in the atmosphere. Now, whether you get an absorption line or emission line in this stratified atmosphere depends upon the source function as a function of height. The source function for this iron 1 line decreases as a function of height, so we have an absorption line. And as we move over the hot granular center of the granule, the temperature gradient increases. So the contrast between the continuum intensity and the line core intensity is the largest. The deepest spectral lines occur there. In the intergranular downflow lanes, the temperature gradient is smaller. There's also velocities moving, for the plasma moving away from us. We'll see a red shift in the spectral line coming up soon. This red dot shows spatially in this continuum intensity for this iron 1 emission line, or sorry, absorption line, where we're probing in the atmosphere. And as we continue to move on and scan across this granule, you can see how the spatial distribution of the spectral line will change. It's not much drastic changes now, but once we get to this magnetic region, all hell will break loose.
What are those great lines that appear sometimes?
So the thick black line is the current position. The less black grayer line is the previous position, and the grayer line is previous before that. So you can see the evolution as a function of position. And so the point is that we saw these nice line profiles spatially and temporally average, but when you look at the spatial variation, it's huge. And when you get to the granules versus the intergranular lanes, it changes. And actually, we have a blue shift here because there is actually upflows. The magnetic field itself has modified the local flow pattern, and there's actually some turbulence going on, in addition to what we would expect in terms of Zeeman broadening. And this is part of the reason why the line is less deep on average. So this is a lot of intricacy that is normally washed over, but it's a lot of hidden physics. So as future observations increase in their spatial, temporal, and spectral resolution, such as the DKIS Solar Observatory that will be out in Hawaii, we'll obtain more and more and better constraints on how magnetic fields affect spectral line formation. Thank you. Yeah, with the Parker probe. It's exciting times. Yes.
Do you foresee some news coming out of Parker in the future? Anything exciting we should expect?
I'm particularly interested in some of their in situ measurements as they get closer to the outer atmosphere of the corona, because as many of us in this room know that stars that have the mass similar to the sun, unless the outer atmospheres are hotter than the surface. And so these in situ measurements will provide strong constraints on what we think could be possibly occurring for heating mechanisms, and also the variations in the solar wind. So I'm really excited. Kelly Corrick works in SSXG. She'd be one of the point people to talk to about recent updates. I don't know if they have any embargoes or anything about what they can say or cannot say.
Well, it doesn't matter. We invite her.
Yeah.
She doesn't even.
Does the typical disk center spectrum that a lot of people use in these fields, does it contain enough independent cells so that the time variability signal we see here is washed away from all the independent cells that are averaging out?
So when you say independent cells, you mean spatial locations?
Well, I mean these like granulating cells, the convective cells. You know, in the disk center average spectrum, you've got n convective cells.
Mhm.
N large enough when you average over.
Yes, that's a great question. In terms of the direct magnetic effect, Zeeman broadening, that's actually the strongest because spatially each position, depending on, for this numerical simulation, they're weighted equally. For actual observations, I'm pretty sure there's a PSF, point spread function, so that would vary. But the Zeeman effect has the strongest effect spatially because it has this pervasive moderate magnetic field, which leads to broadening, while the thermodynamic effect, it works everywhere, but it's the strongest in these intergranular lanes. So you're asking me about how many cells should we average over to wash out some of these effects? Is that what you're asking? Well, mine had about 3 or 4 cells. And this effects are, I mean, this is pretty small, 10 to the negative 3. So the question is, what are you investigating? What are you after? We currently don't have enough precision in our observations to directly detect this. DKIS might, the new solar ground-based observatory will be implemented, and that's exciting to see. I think the signal to noise that you need depends on the physics you're trying to investigate and the processes. So I can't give you a generic, I can't give you just one yes, no. So I would say for the analysis like this, it's small, it's negligible for right now. For oxygen, for iron, you have to think about it a little bit more.
Use this yesterday. Yeah, I'll use this yesterday. I know exactly how it works. Yes, please. Oh, that's enough, actually. There you go. Okay. All right, well, thank you very much. My name is Daisuke Nagai. I'm from Yale University, and I'm talking about the physics of galaxy cluster outskirts. Outskirts of galaxy cluster is one of the new frontiers in cosmology and astrophysics. This is one of the rare environments. The galaxy cluster is one of the largest gravitational bound objects in the universe. And this is one of the rare systems where you can actually map out the distributions of stars and gas all the way out throughout the virialized regions of the galaxy clusters. So we can actually start to get a very detailed view of the formation and evolution and structures in those gravitational bound objects, which provides us some insights into how the nonlinear astrophysical formation actually occurs in the universe. And at the same time, it opens up a possibility that we can understand these regions and possibly apply these galaxy clusters as a laboratory for cosmology. So since this is a new area, we set out this project called Omega 500 Simulation Project. This is a large cosmological hydrodynamical simulations with variety of input physics, from non-radiative simulation, adding cooling and star formation, adding additional feedback from active galactic nuclei, and so forth, and do very systematic runs to understand the impact of nonlinear astrophysical structure formation as well as star formation and feedback and how that affects the X-ray emitting gas that we are now starting to probe out to very large radii in these systems. So this is a work that's actually, so in this system, this is a zoom-in simulations of this 500 H-inverse megaparsec box, which gives us about 65 objects for us to actually study the physics of the outskirts of galaxy clusters. So in one slide, this is what we have learned from about the physics of galaxy clusters. And the points I'd like to emphasize today is that the physics of cluster outskirts is quite different from the physics of the cluster cores. Physics of cluster core is where we have been studying much of the cluster astrophysics because these are very bright, the brightest spots that for over the last several decades, much of the cluster physics work has focused on these central regions, and much of the topic has been these issues related to heating and cooling balance in the central regions. Still very active area of research. On the other hand, in the outer regions of galaxy clusters, the physics is quite different. The important physical processes are things like gas accretion, which is responsible for actually the growth and evolutions of the galaxy clusters, and non-equilibrium physical processes that are associated with these virialization process of the gravitational collapse. Here I just listed a subset of some of the physical processes and physical phenomena that we have learned from these simulations. I'll focus on those first 4 and give a quick summary. But before I go on, I have to actually, we have to put this in a context. The outer regions of galaxy cluster is enormous. The typical working definition of outskirts of galaxy cluster is called this R500. This is a spherical region within which the overall density is 500 times the critical density of the universe. But we have recently learned that there's an outer boundary to the dark matter halos of the massive clusters, which is about 4 times R500, typical region that has been probed using Chandra observations. The latest observation, like Suzaku ultra deep observation with Chandra, or even Planck SZ effect, which is probed the outer regions of a galaxy cluster, is starting to actually extend those measurements, getting closer to the splashback radius. One question here is, how about where is the outer boundary of the gas? We asked. Here's what we found in our simulations. This is the locations of a splashback radius in units of R200 mean. Turns out that the locations of the gaseous the accretion shock around the outskirts of galaxy cluster is about a factor of 2 larger than the location of the splashback radius. This was surprising because that the secondary infall model, the simple theoretical model actually predicted that these 2 locations should actually be coincident. We don't know the answer to this question at the moment. Interpretation is still going on. Nevertheless, this is what we found so far from simulations. Again, this is sort of the work in progress, but this has very important implications. Because the accretion region is where the gas is actually accreting and then the gas is shock heated for the first time. And for example, there's interesting shock physics that is associated with this. When pristine gas from the voids and filaments, when they accrete and experience the shock heated for the first time with a very high Mach number, typically the shock actually accelerates the protons and electrons to the same speed. Most of the energy, because the mass ratios of the protons and electrons are differ by factor of 1800. The most of the energy actually goes to proton when they're accelerated to the same speed. Eventually, through the Coulomb collisions, they actually equilibrate. But the outer region, the low density of the outskirts of cluster is so low to the point that the equilibration time scale is longer than the Hubble time. And what that means is that if you compute that, so this is based on 2 temperature simulation where we follow the evolutions of electron and proton, assuming the Spitzer value, so that's no upper limit. The electron temperature could be as low as factor of 20% or so compared to the temperature of the ion. This has an important implication for those of us who are actually using things like microwave observation, Sunyaev-Zoldovich effect, or X-ray observation, which are mostly probing the temperature of the electron, not the temperature of the ions or the mean temperature. However, when you do simulations, we typically assume a single fluid. When you do hydrodynamical simulation, we're assuming that the electrons and protons are in equilibrium. So that's this effect that usually is neglected in hydrodynamical simulations. Another thing we have learned is that the importance of the turbulent bulk and gas motions in galaxy clusters. And because the galaxy cluster formed through the accretions and merger, that the significant fraction of energies are actually in these motions of gas. In the central regions around R500, where we are doing the cluster mass estimate, the fraction of non-thermal pressure support due to turbulence and gas motions at the level of about 5 to 20%, depending on the dynamical state of the galaxy cluster, or more specifically, the mass accretion rate of the galaxy clusters. And then that this non-thermal pressure fraction increases very rapidly, showing that the significant fraction of the energetics in the galaxy clusters are actually in the form of gas motions. In fact, in a recent attempt, there's actually a simple way of understanding this by actually based on the generation of these gas motions, counteracted by the dissipation, and the balance of those two ultimately determines the distribution, the radial distribution, non-thermal pressure fraction, and that simple model, given the mass accretion rate that you can measure in in-body simulations. In lambda CDM universe, you can predict what this function should look like, depending on the mass accretion history of the cluster of the dark matter halos. So we have a simple understanding of what this might actually be. And then the last, another recent work that's done in collaboration with a member here at ITC is to ask these questions. Based on this, now that the outer regions of galaxy clusters are well modeled in hydrodynamical simulations, can we apply the machine learning technique to actually calibrate the cluster masses in using this latest technology, AI-based technology? The answer is that yes, if you actually, this technology is very powerful enough that, for example, the mass estimation based on the machine learning actually gives us something of order 8 to 12% scatter. For any given clusters, the machine learning can predict the mass of the galaxy, simulate the galaxy cluster at the level of about 10%. This is a significant improvement compared to 15 to 18% scatter that you can get from the state-of-the-art estimation of a cluster mass based on X-ray luminosity. This is a very important implication for things like next generation eROSITA survey, which is scheduled to launch next year, which will detect 150,000 objects out the redshift of 1.5, and the luminosity is the main technique for measuring or gaining an understanding of what the cluster mass estimate is. In this work, the lead author, Nishanta Mupaka, who's here at the ITC, have actually looked into what is actually causing or what is actually teaching, what information in these X-ray images of the simulated clusters is actually helping to improve the scatter or our ability to estimate the galaxy clusters. And it turns out that it's learning on the structure, the gaseous structure in the outer regions of the galaxy clusters. The question here is, what is that convolution neural network, which was used to actually do this training, is learning on? There are two things that I like to that we can learn some insights into the structure in the outskirts of galaxy clusters. The first is the clumpiness in the outer regions. The simulated cluster typically exhibit those clumps and also density fluctuation in outer regions. You can actually take the radial shell of these galaxy clusters and look at the distribution of density at any given radius. What we have learned is that the density distribution consists of two parts. Simple log normal Gaussian parts, which are the volume filling component, composed along with the high density tail that are associated with the small clumps that we can actually see. So there are by excising the very high density tail, we're still left with the density inhomogeneity that are filling throughout the intercluster medium. And the last point is that in addition to the density fluctuation, there's also temperature fluctuations. This is the area that we have not yet seen much convergence among different types of code. For example, if you take this SPH code and AMR code, these are two types of hydrodynamic schemes. The density fluctuations in galaxy clusters have converged between those two. However, temperature fluctuations, as you can see in those images, that is a temperature map from SPH code, which seems to show the significantly enhanced temperature fluctuation compared to one in the grid-based code. So the temperature fluctuation differs by nearly factor 2. And in fact, that was one of the reasons why we're actually getting a different prediction on things called hydrostatic mass. The mass of the galaxy cluster based on hydrostatic assumptions. However, the hydrostatic equation actually takes into account these temperature information, which differs depending on which code you use. So this is something that we need to keep in mind, but those are the two components. Gas density and temperature fluctuations are the things that are actually determining the X-ray emission in the outskirts of galaxy clusters, and the machine learning is actually learning how to actually use those information to improve the cluster masses. So I'll stop here. I'll summarize that the outer regions of the cluster is a new territory for structure formation. The physics is actually sufficiently simple that we can actually hope to learn. These are mostly the gravitational and hydrodynamic problems. Of course, it has the magnetic field, so these are added complication, but some of the physical processes may or may not depend on some of these additional physics that we have not yet explored. So the outer regions of the cluster has the potential for applying for cosmology, and this is one of the ongoing program that we'd like to extend and learning more about the structure formation of the universe using cluster as a probe. Thank you very much. Yes. I think we're gradually moving in that direction, trying to understand what deep learning and machine learning can do for us. In some cases, we can actually get some improvements. Sometimes we don't know why, and I think it's very important that we take this both physics-based and data-driven type approach. Both are probably equally important, and sometimes the machine learning can outperform what we are already doing. But we will, as a physicist, we also like to understand why we're getting. And that these new results are inspiring us to dig deeper into what is happening in these outer regions. In this case, we're digging deeper into what the density and temperature fluctuation, how does it actually informing the machine learning approach to do. And so hopefully there's the more connection between those two approaches as opposed to just doing one or the other. Absolutely. So they're strongly correlated. Typically in galaxy clusters, the pressures, most of the density fluctuations are in pressure equilibrium because the sound speed is very fast, typically thousands of kilometers per second. So if you have the low density region, the temperature would have to be high in order to keep most of these structures in a quasi hydrostatic equilibrium. So there's a strong correlation between those two components. It's similar. Yes.